Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's biweekly contest, Frog Jump 2. The problem states that you are given a zero-indexed integer array, stones, where stones the position, the value at position I denotes the position of the ith stone. So there are a lot of stones like this, and stones of I contains the positions of each of these stones. Now there is a frog and the frog needs to jump all the way to the last node, to the last stone, and then jump back all the way to the first stone. Now there is a constraint that the frog can jump to a stone only once. Okay. Now what is the length of a jump? Length of a jump is considered as the difference between the position. That's it, right? So if frog jumps from this stone 0 to stone second, the length of the jump would be 5 minus 0, which is 5. Now the cost of this entire journey, like going forward to the last stone and then coming backward to the first stone, is calculated as the maximum length traversed, maximum length jump by a frog. So in this particular example, the frog takes a jump of 5, then 1, then 1, and then again 5, and then 2. So the maximum length jump is 5, right? So the cost of this entire journey is 5. Now you are asked to find out the minimum cost of a path. So this is the path, right? And you need to find out a path which have the minimum cost. So how to solve this? Now let's try to again think logically and build the solution from scratch. So we need to find out the minimum cost here, right? Now what can be the minimum cost? The best case can be 1, right? Like 1 is the minimum cost. Why 1? Why not 0? Because it is given that the stones are the stones value are strictly increasing. So minimum possible value, a minimum possible cost can be 1. Now let's say now what let's say you need to verify whether 1 is possible or not. So what you want to solve here is whether cost of 1 is possible or not in the given configuration, right? Similarly, let's say cost of 1, let's say you solve it somehow, like we need to think about it, but let's say we solve it somehow. So if 1 is not possible, we will try with 2, right? Again we'll see if path 2, if cost 2 is possible or not. That is, if a frog can jump at max 2 length, whether it is possible for the frog to complete the entire journey or not. Again, if 2 is not possible, you will try with 3, and the first place where it is possible, that will be your answer, right? So what's the problem statement now? The problem boils down to figure out, given a cost, whether that cost can be possible or not. Or in other words, given a cost, find out whether frog can complete the entire journey by taking all the jumps which is less than or equals to the given cost. Okay, so let's say the cost is C. Okay, so and for example, let's consider the C equals to 5 for this particular example. So what we are solving is, given a cost C, tell me whether cost C is possible or not, because we just saw that to just do even brute force, like just to find out the solution in very brute force manner, we need to solve this particular problem. We can't escape from this problem, that given a cost, tell me whether this cost is possible or not. So let's try to solve this. Now frog is initially at stone 0, right? Or the first stone. Now there are, like, you know that you can the frog can jump maximum length of 5. So currently there are two possible jump. Either the frog can jump here or frog can jump here, right? Frog can't jump here because the length would be 6 now, like 6 minus 0, which is 6. So there are only two possible jump. Now which one frog would take? Like which one of these frog would take? The answer is the second one, or the longest one, basically. Why? The reason is the given constraint that you cannot jump to any stone more than once. So if you know, like, if you know that you can make a jump of 5, right? Like, we already assume that we are already trying to find out whether cost of 5 is possible or not, like cost equals to 5 is possible or not. So we know already that we can make a jump of 5. So will, like, if we make a lesser jump, we would be visiting one more stone, right? And in a way we are restricting our path while coming backwards. Like, if we visit this node, right, let's say if we visit this node, then while coming backwards we would have one less choice because this node was already visited, right? And it, like, let's say frog can jump somewhere, like from somewhere to here, but because we have visited this node, now the frog has to jump somewhere to there, which is like longer length, and the cost may increase. So that's the idea. Now some of you might still be thinking that, okay, uh, I get this part, like, I know that if a frog can jump maximum length, it should jump maximum length, like it should try to jump greater length rather than smaller length. But what about the case where, uh, if frog has jumped, let's say, okay, let's, so there can be cases, like some of you might be thinking that there can be cases like frog jumps here and then from here to here and then to there, so that while coming backwards this 5 is available, right? Some of you might be thinking this, but this is also not true. Like, s- what we just said, or what we just like try to prove is, if frog has two choices, like initially frog has two choices, either this or this, right? And what we are saying is frog will always take the largest choice. Now we are trying to prove that part. Now we kind of proved that, okay, in backward jump, taking, taking as less stones as possible would be optimal, right? But we can take a smaller jump and then take a bigger jump, right? And so that we skip some stones so that this stone can be used in reverse journey. That can also be the case, but this is not possible. Let's try to prove that as well. So let's say, what you are like let's say you have two choices. You have two choices. One, you can move from here to here, right? And second, you can move from here to here, right? Now what you are saying is, and let's say while coming backward, this is the last stone, right? And while coming backward, you know that this is your maximum length possible, like you can't jump greater than this length. So you have to jump first here because there is no other stone at all, right? So you have to jump first here. Now think about it. Like, you first jump here from here. Now can you jump forward to this stone directly? No, right? Because you have to jump to this stone anyways. So in a way, you are restricting yourself only. Like, so what we are trying to prove now here is, if we go backward, like if we skip some stone here, and that stone can be utilized in the backward journey. But with this picture, what we are trying to show that, if even if we try to do so, that will not be optimal because we would have to visit that node in the forward journey itself. So for example, let's say this is the maximum length that frog can jump, right? Now if this is the maximum length the frog can jump, if I am saying that for backward journey, I want to save this particular stone because I know there is no other stone that frog can jump in the backward journey. So if I want to save this stone, and that's why I made this jump first. That's the argument, right? We want to save this stone, so we jump here. So can we jump directly from here to here? The answer is no, because you can see the maximum length is this much only, right? So from here to there, this might this like this much length would be possible. So you have to make this jump in the forward journey itself, right? So if you are making this jump in the forward journey itself, then in a way you actually worsen the scenario. Like you took one node extra, which you could have avoided, right? So all in all, like if you're not clear with this part, I would strongly encourage you to rewind the video for a minute or two, and I'm sure you will get this part. So basically, what we are trying to show here is, if there are two choices, the frog will always took the largest choice always. Okay. Now we need to find out whether the cost of 5 is possible or not. So what we will do, we will start from 0, we will make the largest jump possible. Now how to make the largest jump? Just start iterating from 0 index, go to first index, see if this jump is possible or not. If it is possible, go to second index, see this jump is possible or not. If it is possible, go to again for move forward, see if this jump is possible or not. This jump is not possible, so this is your first jump. Like you will make the first jump to here. Now once you make this jump, just mark this node visited. Let's say this underline is marked node. Now you mark this node visited. Now again you will try to jump the maximum one. So this is your maximum jump, right? Now during backward journey again you will do the same thing. You will Now this 7 is visited, 5 is visited, right? Now during backward journey you will try to make the maximum jump first. So here you will see, okay, this 6, is this 6 like possible? Yes, the jump is 1, so it is possible. Now you will say, okay, it is possible, so let me try a bigger one. You will go to 5. Now 5 is already visited, so you know you don't visit this. You go to 2. Is this possible? Answer is again yes, it is possible. So you will try again a bigger jump, which is to 0 directly. It is not possible. So that's where you will just go to 2, because 7 minus 2 is 5 and 5 is still possible. So you go to 2, mark 2 as visited, and then again from 2 start the same thing and you will end up at 0. So if you are able to complete this entire journey, then we can say, okay, the cost C is possible, right? So once we have solved for a particular cost, what we have to do, we just need to iterate starting from 1 all the way up to n, and just see for each of them whether the cost is possible or not. So let's just first look at the pseudocode. We will look at this complete solution again. So the pseudocode would look something like this. So what we are trying to solve is whether a particular distance is possible or not. Okay. So we first start with the forward movement, and what we are doing, we are just finding out the largest j. We start from 0. We are trying to find the largest j where array of j is less than equals to distance plus array of index, right? So we are just iterating from current index to the rightwards, and just checking whether what is the largest j possible which satisfy this condition, right? Now there may be cases where there is no such j. For example, in this case, if c is 1, then you can't make first jump itself. So if that's the case, like if index is equals to j, that means you can't have any such j possible, you will return false, because you can't make the jump at all from this particular position. So you will return false. Otherwise, you update your position to that particular index, mark that position as visited, and continue the same process. Now, once you reach the index n, once you reach the largest in like the last position, you will start your backward journey. Now, backward journey would be again be similar. You will just try to find the smallest j, where array of j is greater than equals to array of index minus distance, right? And there is one extra condition. Extra condition is visited should be false. Like there are some nodes which you have visited in the forward journey, so that those nodes should not be considered in this backward journey. Now to to do this as well, you just need to iterate backwards from starting from the largest index. So once you reaches 0, it means you have completed a one like the entire journey with maximum length of distance. So the answer is true, like it is possible. Otherwise, the answer is false, right? Now, what is the time complexity of this entire this entire algorithm? Order n, right? You are iterating from forward to backward once and then from backward to forward once, right? So order n is the time complexity. You don't need any kind of binary search or anything here, just iterating from forward to back, like first from left to right at each index and then from right to left at each index, right? So once you understand this, right, like once we found out that okay, whether C is possible or not, like we are able to answer that whether a particular cost C is possible or not. So what is our algorithm now? We will see okay whether one is possible or not. If it is not, we will see whether two is possible or not. If it is not, we'll see whether three is possible or not, right? And so on and so forth. The first one, which is possible, we will return that value as an answer, right? So that is like that is the approach. But now if you, what is the time complexity of this approach? The time complexity would be the largest value of this x, which let's assume that it is some c, the largest value of c multiplied by n, because for each cost you are, like you are iterating over, like you are applying this particular algorithm, right? So the complexity would be c into n, right? Now will this pass? The answer is no. The C, which is the maximum cost possible, is 10 to the power 9, and n is 10 to the power 5. So it will not pass the time complexity. So what exactly we can do to optimize here? So notice that we are doing a linear search here, right? We are seeing that whether one is possible, then two is possible, then three is possible, and so on and so forth. So the first thing that you should apply here is, or you should think about, is binary search. So what exactly binary search is? You have some sample space. I have a very detailed video on binary search already in the channel. I will link that in the description and the comment section below. I would encourage you to check that out. Uh, like after this point, if you have watched that video already, after this point, the entire solution would be very straightforward. So now what you like what binary search is, first of all, you divide your sample space into two particular two halves. Now if you are able to say deterministically that whether I need to search either in right half only or in left half only, right? So if you are able to say this deterministically, then you can apply binary search. Now what is the function here? The function here is, let's say, 1 2 3 and so on and so forth up to some c, right? So let's say at some particular point c, you are checking whether c is possible or not, whether you can make a jump, whether a frog can make a maximum jump of c or not, like whether the frog can make maximum jump of c and complete the entire journey or not, right? Whether this function is possible or not. If let's say it is possible, like frog can complete the entire journey by taking a maximum length of maximum length of c, then will you need to, or do you need to search in the right half at all? The answer is no, because you want the minimum value, right? And you know, if c is possible, c plus 1 is also possible, c plus 2 is also possible, right? So you don't need to search in the right half at all, you just search the left half. Similarly, if answer is false, that means if frog cannot complete the entire journey by taking a maximum jump of c, it means frog has to make more jumps, like more larger jumps, because this smaller jumps, with this smaller jumps frog can't complete the entire journey. So checking any of these would not make sense. So in that case you will only check in the right half. So there are two cases. If at middle position the value is false, that means frog cannot complete the entire journey, then you will search in the right half. If the value is true, frog can complete the entire journey in this particular c, then you will search in the left half. Okay, so that's the entire algorithm. Now what will be the time complexity? Now instead of this c, you are not iterating over every samples, like every possible sample space. Instead you are iterating over log c of them, right? So the complexity would be log c into n, and this will definitely pass the time complexity. Okay, so Like this entire algorithm is very straightforward, so I'm not implementing it at all. And the second piece, which is this binary search, is also straightforward. I would encourage you to code the solution yourself, and I will link the sample solution in the description below. You can check it out if you want to. Hope you get the solution. If you have any doubts in this entire problem or the thought process of how we reached to the solution here, please post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe to the channel if you haven't already. And I will see you in the next one. Thank you.